Good afternoon, everyone. Welcome to the second session of my course. So let me remind you about the title of the session. That is on the role of group theory in coherent state and the coherent state quantization. And session 2 is about generalized coherent states. If you do remember, session 1 was about canonical coherent states. So now for the second session, we'll see how one can get generalized coherent states. So so let me start with giving you an outline of the session 2. So session 2, right? Session 2, generalized coherent state. Okay. I will first start by giving generalized vector coherent states. Then I will talk in the second part of the generalized coherent states from a Lie group. Then in the third part, I will give some examples of generalized coherent states. A first set of examples will be given. And as an example, I will give the spin coherent state or it's also called the group SU2 coherent state. Then a third set of examples will be about the group SU11 coherent states. Okay. So this is basically the content of the session 2. So let me start then with generalized vector coherent state. Let's start with a possible general definition of coherent states. Let H be an abstract separable Hilbert space over the complexes okay. Let X be a locally compact space and d mu a measure on X. Let the vector X I be a family of vectors in the Hilbert space H defined for X in the compact space X and indexes I that goes 1 to n, where the number n is usually finite, although it could be also finite. It could also be infinite, but here we assume it is finite. Okay, we assume that the set of vectors that I rub inside possesses the following properties. So, a first property would be property 1 for each index I, the mapping X goes to vector Xi is weakly continuous That means for each vector phi, in the Hilbert space, the function phi I x equal to the overlap xi y is continuous, and that in the sense of topology on X. So this is the first property of our set vector xi. The second property is that for each element of the locally compact space X, the vectors xi are linearly independent. And a third property of these vectors is the resolution of the identity. What does it mean? It means that the summation from I goes to 1 n of the integral of the x of the projection xi d nu x is equal to the identity of the Hilbert space H. So that identity holds in the weak sense in the Hilbert space H and that means for any two vectors phi psi in H, the Hilbert space H, the following equality holds. That is the sum for I goes from 1 to n, the integral x, the overlap phi xi vector xi conjugate psi d mu x is equal to phi psi. And you can also start the other way, that we overlap phi psi, then you insert the resolution of identity, so that will give you that. So this resolution of identity in the weak sense also gives the last expression I've just written. So now a set of vectors xi satisfying the above three property is called a family of generalized vector coherent states. So let me state that a set of vectors xi belong xi 1 n satisfying the above three properties is called a family of generalized vector coherent states. So this is an abstract definition of generalized coherent states. Now, for n equal 1, if you have only one vector, then the set is called a family of generalized coherent states, not vector but coherent states. Okay. Sometimes the resolution of the identity condition is replaced by a weaker condition with the vectors xi simply forming a total set in the Hilbert space H. And the function fi x defined as the overlap xi phi as Fi in run through the Hilbert space H. Okay. In that sense, we have the sum I goes from 1 to n, the integral over x of the projection x I x I xi d nu x equal to the identity in the Hilbert space is immediately seen to apply that vector phi is equal to some I goes from 1 to n, the integral over x, fix on the vector xi d nu x, where we have fix is equal to the overlap xi from. Okay. This is in weak conditions, okay, replacing sometimes the resolution of the identity conditions. Okay. So let us now start with the second part, that is how to get generalized coherent state from a Lie group. Okay. Because what we have seen first as a generalized vector coherent state is defined is an abstract definition. We get set having a Hilbert space, a locally separable compact space X. Okay. Now let's see in second part generalized coherent states from a Lie group. As we have already seen in session 1, if you remember, session was canonical coherent state. The canonical coherent state can be described as the set of vectors resulting from a unitary irreducible representation of the Weil-Heisenberg group. This process can be applied to an arbitrary Lie group and define the notion of generalized coherent states. Let us now define the notion of generalized coherent states in the sense of parallelomorph. So I will state it as follow. Generalized coherent state. Let's define that. Suppose we have a Lie group G with a unitary irreducible representation that I'll call T of G. On some Hilbert space H, not necessarily square integral. So my Hilbert space here do not need to be square integral. If we take a fixed vector psi naught, let's call it psi naught, of unit norm, we define the coherent state system that I T, the representation, psi naught, fixed vector, to be the set of vector psi in H such that psi is equal to T J psi naught for some element J in the group D. Okay. This is how we define the coherent states system, representation T and a fixed vector psi naught such that the set of vectors on the Hilbert space H that are defined by psi equal Tj psi naught, and J is an element of the group capital G. Generalized coherent state are defined as the states psi corresponding to these vectors that I denoted psi in the Hilbert space H. So this is how we set the definition of generalized coherent state. Now it's important that we check the parametrization of the generalized coherent states and how to have or to choose the fixed state psi naught. Now, let's check parametrization of the generalized coherent states and how or choose the fixed state, or let's say the fixed state. So, okay. In order to do that, we'll proceed as follows. Let's define the subgroup H of G consisting of all elements H in G that leaves the fixed vector psi naught invariant up to a phase theta. So in that sense, what is then our subgroup H of G? It is in a compact way, we can say H is the set H element of G such that T, remember T is the representation H on the vector psi naught is equal to exponential I theta psi naught or some theta that belong to the interval 0 to pi. Okay. So H corresponds then, the subgroup H corresponds to those elements of the group G such that the state TG psi naught equal the state psi naught. And H is called in that way, H is called the isotopy subgroup of G. Once we set our subset H, now let's consider X equal G modulo H, the left coset space If G1 and G2 belongs to the same left coset X, then we can write that G1 is equal to G2H for some H belong to the subgroup H. And with that, we would have, you can check that also, that's possible. We would have G1, G2 minus 1 is equal H, a certain H that belong to the subgroup H. And what does it mean? That G1, G2 inverse belong to the subgroup H. It implies that we have T G1 G2 inverse psi naught is equal to certain exponential I theta psi naught. This is the characterization of element of the subgroup H. And that means the corresponding vector of G1 and G2 differ from a phase and hence define the same physical state. The sense that we will have state T G1 psi naught is equal to state T G2 psi naught. So if we have two elements G1, G2 that belong to the same left coset to all X, then they will define the same physical state. We can parameterize then the set of coherent state by the element of the coset space X as follows. Okay, so we can Consider an arbitrary element choosing a coset representative Gx capital G for each coset x, we define vectors x is, this is the vectors. Maybe I can also call it the state, doesn't matter. Gx and these are called the Gilmore Lomov coherent states. So this is what we call Gilmore-Perelomov coherent state. Okay. So since the representation T is irreducible, the set of the coherent state when X runs the coset is dense in H. In this definition of this first point, second point, in this definition of generalized coherent states, no resolution of the identity is postulated. Okay. Now, an important question is questions how to select the fixed coherent state or in another way, how one choose or select the fixed vector psi naught. In the definition of a generalized coherent state, we have made no requirement on the fixed vector psi naught, or if you want on the state psi naught. In principle, any state in the Hilbert space can be taken and generate a system of coherent state but in physics, the preference is to consider the coherent state of a state that is closest to classical state. So for how to choose a fixed vector psi naught, any state in the Hilbert space can be considered, but as I just said, in physics, maybe it's better to choose the fixed state as a state close to the most close to the classical state. So this is what we think. Now let us start with some examples. Okay, let us start with examples of generalized coherent states. And as I already said in the beginning, for those examples, I've chosen three examples. The first one is a set of examples, okay, that are derived from a generalization of the canonical coherent state. And then we'll have the spin coherent state or the group SU2 coherent states. And then we'll have the Baruch-Giraldello coherent state. So let us start with our first set of examples. First set of examples. A simple modification of the analytic structure yields a large class of generalization of the coherent state. That we here remember in session 1 we have defined those canonical coherent states. So we want to have a large class of generalizations of these type of coherent states that we have seen in session 1. Let x1, x2, xn be an infinite sequence of positive numbers with x1 different than 0. Setting xn factorial is the product x1, x2, xn, and by convention x0 is 1. Okay. if we set that in the same Fock space, in which the canonical coherent states were described, we now define the related deform or nonlinear coherent states via the analytic expression. Or expansion is better. Expansion. That is Z is equal to normalization factor that depend on the modulus of Z square sum n goes to 0 infinity Z power n divided by xn on n, where the normalization factor that is n is chosen such that okay, what are the properties of these coherent states? Okay. Let's see the properties of these coherent states. There is the over completeness in the Fock space and the and resolution of the identity of the type the integral of a D, we see what is D, of the projection operator ZZ, normalization factor D nu Z conjugate Z is equal to 1. Okay? And as I said, D is defined as an open disk in the complex plane of radius L. Okay? And D nu measure Z conjugate Z is, sorry, is equal to 1 over 2 pi d theta d lambda r when we take Z as r exponential I theta and d lambda n is related to xn as follows. The relation xn is the integral 0 L r power 2n d lambda r for n goes 0, 1, 2. That's called the moment condition. Maybe you can try to check that as a good exercise. So this is a first example of generalized coherent state derived from the canonical coherent states. A second example, and also a nice one, second example, second examples. So a second example is what is called the gaso-cloud coherent states. The gaso-cloud coherent state. How do we describe the gas-cloud coherent state? That is also a generalized coherent state. A non-analytic extension of the expression Z is sum n goes 0 infinity Z power n xn is often used to define generalized coherent state associated to physical Hamiltonian having pure point spectra. So these coherent states known as gas-cloud coherent states are labeled by action angle variable. Let us see uh, how these states are completely defined. Suppose we are given the physical Hamiltonian H is equal to the sum n goes 0 to infinity En projection vector n with E0 is 0. It has an energy En and eigenvectors n, which we use to form an orthogonal basis for the Hilbert space of state H. Okay. Let us write the eigenvalue as En equal omega times epsilon n by introducing a second of dimensionless quantities that will denote epsilon n ordered as 0 equal to epsilon naught smaller than epsilon 1 smaller than epsilon 2 smaller than, okay. Then for all the positives and gamma real, because Laure coherent states are defined as state G gamma equals to normalization depending of G, some n goes 0, infinity, G power n 2, exponential minus I epsilon n gamma divided by square root of epsilon n factorial. We have already seen this notation with the first example on the state n, where n normalization factor n depend of G and okay. So this is what is called the gaso-cloud coherent state. So some properties of this coherent state is that we have the exponential minus I Hamiltonian T on the state J gamma is the state J gamma plus omega t. And check that. And the action identity is the mean of the Hamiltonian and the state J gamma is equal to omega d. Okay, so you can also check, and in the references that I've given in session 1 at the beginning of introducing generalities about coherent states. In my references, if you read, you can have more information in the gaso-cloud coherent states. Also, in the literature, there are many articles relating about this wonderful setting of coherent state done by Gazo and Clouder that I am lucky to have known both. So let's now see another example of generalized coherent state, and I call that, so this is 3B spin coherent state. You will see that for the first set of generalized coherent state, we didn't mention anything about groups. So it comes from inspiration of a canonical coherent state and a generalization. So now for the spin coherent state, you will see that it has to see with groups. And in fact, the spin coherent state is also called the SU, the group SU coherent state. So let's consider the coherent states of the group SU2, which in physics are often referred to as spin coherent states or atomic coherent states, or it's also called block coherent states. So this first point, the SU2 coherent state were introduced in the early 1970s by Radcliffe, Gilmore, and Perry Lawrence. But before I pursue with SU2 coherent state, let me briefly recall the group SU2. The group SUN, let's start with SUN, is called the special unitary group of dimension n. Okay. N is defined as the group of n times n unitary matrices with complex coefficients of determinant 1. For example, for n equal 2, we are in 2 dimensions. It consists of the matrices A is equal to A minus B star B star, where we have absolute values of A square plus absolute value of B square is equal to 1. A, B are complexes. Okay. So this is the definition of the group SU. The Lie algebra can be shown to be the real vector space of 2 by 2 complex anti-emission matrices with vanishing trace. So what does it mean? It means that SU2 for Lie algebra, you see we use small s small u. For a group, we use capital S capital U. So SU2 Lie algebra will be the set of elements of GL, or define what's GL2C, with x dagger plus x is equal to 0. That means that's the definition of the trace. X is 0. So let me give you what we mean by GL2C. where GL this notation to C is the vector space of the 2 by 2 inversible matrices of complex coefficient. It is the Lie algebra of the general linear group GL2C. So G GL2C is the Lie algebra of the general linear group GL2C. So now we consider a spin G, this is where spin comes in, that's positive, okay? Representation of the algebra SU2, that's included in SL2C, and set its generators as G plus, G minus, G3 with G plus dagger is equal to G minus and satisfying G3 G plus commutator is equal to G plus G3 commutator with G minus is minus G, and the commutator G plus G minus is equal to 2G. So these are the commutation relation between the generators. Let's note that for unitary representation, for unitary representation, it is necessarily finite dimension. Yes, finite dimension. But in a good way. The Fock space on which the generator G plus G minus G3 act is HG, the set of vector G M if 0 smaller or equal to M smaller or equal to 2G. And the actions of the generators on the element of the Fock space are the following. We have J plus act on Fock element Gm as square root m plus 1 2J minus m on the state J m plus 1. The generator J minus on the Fock element Gm is square root m times 2J minus m plus 1 J m minus 1 J3 on J m is equal to minus J plus m Jm. Okay. So the vector, there is this vector J m equals 0 is a normalized vacuum in the sense that we have J minus J0 is 0 and the overlap J0 J0 is equal to 1. That is the normalization condition. So we have written, let's remark that, we have written J0 instead of 0 like in a canonical coherencies, emphasize the spin J representation. And the notation is the unit operator on the Fock space G. Now, how do we define our generalized coherent state that we call SU2 coherent state? So, definition, we call a state that says V equal to exponential V J plus minus V bar J minus on the normalized vacuum 0 for V, a complex number, the generalized coherent state based on the Lie algebra SU. This is our definition of generalized coherent state, and this is actually how we define the spin coherent state or the SU2 generalized coherent state. Okay, so this is as you see, those coherent states are built using Lie group, Lie algebras SU. Now, let me give the last example of generalized coherent state. the group SU1 coherent states. The SU1 coherent state also called pseudo spin coherent states were established by Lamov in a group theoretical approach. There exists another family of coherent states associated with the group SU1 called the Barut-Girardello coherent state. But let us first recall the Lie group SU11. Okay? Let's first recall the Lie group SU11. SU11 is the group of matrices of the form alpha, beta star, beta, alpha star, such that modulus alpha square minus modulus beta square equal to 1. Okay. This Lie algebra that will denote SU11 can be generated by vectors K1, K2, K3, okay? Satisfying the commutation relation K1, K2 minus I, K3, K2, K3 is equal to I, K1, and K3, K1 is equal to I, K2. So this is the commutation relations of the generator of the Lie algebra SU11. K1, K2 is minus I, K3. K2, K3 is I, K1. And K3, K1 is I, K2. So we don't stop for the generator K1, K2, K3. A different basis of generators can be chosen, like K plus minus is equal to K1 plus minus I, K2, in which is the commutation relation become K minus K plus is equal to plus 2K3, K plus K3, K plus minus is equal to plus minus K plus minus. So this is a redefinition or this is another setting when we consider another basis. And the representation of the Lie algebra SU11 on the Fock space is generated by K plus K minus K3. And the generator K plus K minus K3 act on the vectors n of the box space as follows. K minus n is equal to square root n times 2 kappa plus n minus 1 on vector n minus 1. Here kappa is me with let me not make confusion, is take values like 1, 3 over 2, 2, 5 over 2, kappa. Okay. And we have k plus is equal k minus dagger. So if you know the action of k minus, you then know the action of k plus. K3 is equal to kappa plus n on n. K minus on the vector 0 is 0. And with that expression of vector n can be given as 1 over square root of factorial n 2 kappa n a plus n 0. So here the notation that you have here of the notation you have here of 2 kappa n, I will give that as we have if you have this a parenthesis this notation means is equal to gamma, like gamma function, a plus m divided by gamma a, and this can be expanded as a times a plus 1 times a plus 2 times a plus m minus 1. This is just definition. And then, as I said in the introduction of the SU 11 coherent state. I will give rather the definition of what is called the Baruth-Girardello coherent state. The Baruth-Girardello coherent state Z are now defined as the formal eigenvectors of the ladder operators K minus as K minus Z is equal to Z, Z, Z belongs to C. Okay. The analytic form of the Baruth-Girardello coherent states are given by Z state Z is equal to modulus Z power 2 kappa minus 1 over square root of E. I will give this notation later. Index 2 kappa minus 1 of E is a modified Bessel function that I will give of argument 2 modulus Z. Okay. Sum n goes 0 to infinity, Z power n divided by square root of factorial n 2 kappa plus n minus 1 over n on the vector n, where E nu x is the order nu modified Bessel function of first kind. Okay. So with the definition of Baruch-Girardello coherent states as an example of generalized coherent state, I stop with the lesson 2, the session 2, I'm sorry. So this is the end of session 2. I hope you did enjoy. And let's meet for the next session, that is the session 3 on the coherent state quantizations. Thank you for listening, and see you soon for the next lesson.